in 478, the line emission spectrum and the Bohr model, work number 1 on the worksheet, ABC. Then number 2A, do 1, 2, 3, 4. When you read the question, you'll see that there's a 2A, I think a 2B, maybe a 2C, I'm not sure. But each one, they want you to answer 1, 2, 3, and 4. 4 things. You can just do number 2A, 1, 2, 3, 4. If you want to do all of them, you could. For more practice, that's fine. Now, this is a pretty interesting thing. And I left on the board the electromagnetic spectrum. But really, all we're going to be looking at here on the electromagnetic spectrum is visible light. And remember, visible light, well, actually I'll put it up here because I'm going to erase this. Visible light can break down into Roy G. Biv. Okay, we know that red, orange, yellow, green, blue, indigo, violet. And as I told you, this is just some numbers they chose along the way, but really one color blends into another. Now I have some colored chalk here. I'll play around with it a little bit. I don't have all the colors that are mentioned, but I have a lot of them, and I'll show you. So, yes, light and color of light will matter in this section. Now, first, there is something called the line emission spectrum. It's also called the bright line spectrum. And is there another name for it? I'm not sure. It'll pop up probably along the way. In the notes, it talks about this, the bright line spectrum. Now, this was discovered, from what I know, in the early 1900s, before the quantum model, and it led to the quantum model. Something interesting. There were 3 big puzzles that were found. One of them was called the line emission spectrum. I'm talking about now. One of them was called the photoelectric effect. I'll do that in another lesson. Then there's another one called black body radiation, which is kind of an interesting thing too. So first, I'll just say it this way. How will I bring it up? I could actually say a little bit about black body radiation to let you know, but what it means is, what it has to do is this, that, well, I better not go into it right here, but when you heat up an object, certain chemicals or certain metals, certain things were heated up in the early 1900s. When you heat something up, we know it can give off light. Okay, well, it was expected that you think, okay, as you heat it up, first it might kind of look reddish orange color. Then it might get brighter like a yellow. Well, you would think that as it gets hotter and hotter, I'm talking about black body radiation. I didn't know I was going to do it, but I guess I am going to say something about it, just to mention it. As you heat that metal piece up or whatever, you know, you kind of get this red, orange, and yellowish color, but then you don't ever see a green or a blue. I mean, you might see a bluish in some flames sometimes, but it kind of skips along the way. You don't see green, or then indigo, and then purple. And then you would actually expect, if you continue to heat it up more and more and more, like a hot coal, or not, I don't want to say coal, but iron. Like, say they're doing iron metal work, any metal crafts or whatever. You would expect that at some point you get so hot that the heat or the light coming off it is invisible. It becomes ultraviolet light. So that has a little bit to do with black body radiation. And I will just, you know, I'm not doing very much justice to it right now, honestly. So I'll probably get back on it later on. But anyway, the point was that there was a gap sort of in the colors. Like, it didn't make sense. If we know the color of the spectrum and then it goes to invisible, when you heat something up really hot, why does the light change to all the colors you see here? Because remember, this is low energy, a photon, and this is a high energy. Well, we know that to be true now. Okay, low energy to high energy. They had some idea about that anyway back then, even before the photon theory. They noticed this. Okay, well anyway, so let's go into the bright line spectrum. Let me move on to it now. I'm gonna bore you with that bit. This black body is not talked about a whole lot at all, and I might go back or check something. Oh, I better leave my Roy G. Biv. All right, so here is the neat thing to bring up. Okay, if you take any element, and we mainly talk about gases, but if you take any element and then you turn it into a gas. Okay, so you take an element, you turn it into a gas, then you put it into a bulb, like a light bulb, okay? So let's just say we have this glass bulb, and you may have seen this. I had some for a while. I showed in UCLA program. But on this side, you'd have electricity coming in, and on this side, you have electricity going out. Now, you might remember back in chapter 2, we talked about the Edison effect. That Thomas Edison found that, hey, if you put electricity, obviously electricity will conduct through a wire if I had a wire there. But if I had no wire, if I removed all the air from this glass bulb, then the electricity, the positive, negative charge, would flow from one to the other side through the vacuum. So in other words, empty space, vacuum, a vacuum chamber. In a vacuum chamber, electricity can flow from, we'll just say, from a positive to the negative electrode. They can do that. Actually, I have it the wrong way. We'll say negative to positive electrode. Okay? From the negative to positive electrode, electricity can flow, electron charge can go from one place to another in a vacuum. Well, if I put a gas in there, like for example, hydrogen gas, and I'm going to play with the chalk here and show you this. Okay, I'm going to take these colors, this color, and why not this? Well, maybe this one will be good. Maybe I'll take this. Okay, so what I'm going to do is maybe I'll pick these. All right, let's see if this will work. So I'm going to color in a color. Well, anyway, the point is the gas, when you put electricity through a gas, if there's nothing else, you take all the air out first of all, but then you put a gas inside there, and the gas will glow a certain color. Now, as I make this color, I'm adding in some other color to it. You can kind of tell. And then I'll even put in a little bit of this one too. Okay, so let me get a little bit more. All right, it's kind of working out. Now, maybe I need a small bit more of the red. I don't know if you can see this too well. You're just thinking, oh, you're just rubbing one color off, another. Okay, but you can actually see something there. If I like cover it up and say, now look, boom, what do you see there? All right, it's a lavender colored light, kind of a pinkish lavender color light. Now, this is the color of light that you'll see if you put hydrogen gas in what's called a gas spectrum tube. They call them gas spectrum tubes. I have some for Venice, or gas emission. No, is it gas emission? Gas discharge. That's what it is. Gas emission tube, gas discharge tubes. All right. So here we go. So you see this color when hydrogen gas is put in. Okay. Now here's and this was known in the early, we'll say early 1900s. They played around, electricity coming into play. They found the electrons, late 1800s. And so someone said, hey, look, if I put hydrogen gas, look at what it does. And it gives you a pink color. Well, it turns out that every element gives you a different colors. It's amazing. I mean, neon is the most famous. So neon actually is like an orangish color, a real bright orange color, the real neon. Now, people say, well, neon lights. When they say neon light, they're talking about a glass bulb containing gas, okay? That, like, maybe it says open or whatever it might say, show tonight or whatever they write on the thing, or so on the little marquee things. Restaurants and all have these things as well. But in a real, what we call a neon light, there'll be gas inside there. If you go close to a neon light, you actually can hear it buzzing a little bit, like bzzz, as the electricity is up there. You can see the gas particles moving. If you look really closely, like a little fog inside there of the colors. Now, the other thing, if it's pure neon, well, then it will be orange. But they use the word neon for any lights, any glass light that has gas inside them. Okay, so we're going to talk about this one. We're going to talk about the hydrogen gas. Now, it turns out, remember we talked about you could take a prism. If you take a prism and you take white light, so let's just say light from the sun, white light comes along, well then you put it through a prism, like a glass triangle kind of shape thing. It could actually be any piece of glass at an angle could do it. A mirror could, or something that can reflect could also do it. You could be in a room and have just like sunlight coming through, and you kind of have a flash a little piece of plastic or something, or glass. Maybe glass is better, and anything shiny, and try to get the light and beam it over to the wall, and you'll notice a rainbow on the wall. Well, what's happening is that plastic you have, or the glass, or the prism, even better, is breaking the white light out into the spectrum of Roy G. Biv. So you see that. I won't. Oh well. I don't want to sit there and do Roy, red, orange, yellow, green, blue, indigo, violet. Like you can't even see them all there. Well, I guess I can do it because I'm playing with it here. Red, orange, yellow, green, blue. Indigo is kind of in between a blue and a purple right there. In fact, what is indigo a lot of times might really be like a purple. All right, but anyway, I'll just put them both together. I don't know if you can see that at all. Roy G. Biv, you can't really see that. It's supposed to be like a rainbow, but you just imagine you get a rainbow, and we call it Roy G. Biv. Okay, so let me put these things together. I keep saying all this random stuff. Like, what is he talking about? Okay, so the scientists decided all these elements. Hydrogen gas has a certain color. Mercury gas. Mercury gives you a really weird, like a mercury vapor lamps are actually used in street lights a lot, and they give, it is a white. It's a white light, but it's kind of I'll just say it's kind of close to a little bit of a silvery, or almost like, I don't know how to describe it. Purple, not really. Can you see purple in it? I'll say maybe a bluish silver color. It's kind of a silver light color with a bluish tint. And anyway, mercury vapor. Helium has its own color. I can't remember right off the bat what that one was. But then every gas you can think of in the chart, and we've got tubes for all of these. Oxygen gas, hydrogen, all of this. Oh, okay. Anyway, back to this. So what we'll do, what the scientists did was they put a diffraction grating in front of this light. So they looked at the light through a prism. Okay. Now there's also something called a diffraction grating, and I think I might just tell you what that is real quick, because we have some of these, and you can hear about them, especially AP could hear about these. It looks like a slide. This will be like a piece of paper, and there's a film in the middle of it. And the film is like sunglasses, okay? Like, think about, have you ever heard of polarized sunglasses? Well, it's very similar to that. But polarized glasses, what they do is, you can't see them, but there's really small lines, like in your sunglasses. You can't even see them at all. But what it does is, it blocks out certain light. Some wavelengths can't get through, like the ultraviolet can't get through the way the lines are. All right, in a polarized lens, polarized sunglasses. Well, in a diffraction grating, the lines are even closer than that. They're really, 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 really close. I couldn't even show you. I mean, I'm just kind of, looks like I'm just shading it in right there. But you can't see the lines. So if I were to give you a diffraction grating, you would just think, oh, it looks kind of like grayish, like a gray sunglasses. But it's going to be blocking out and splitting up the, it will do the same thing that the prism does. It will split the colors up into the spectrum. Okay, so if I shine white light through a prism, I'm going to see a rainbow spectrum. I didn't do a very good job of making a rainbow there. Actually, I guess it looks better when I kind of did that. If I shine white light through a diffraction, well, how about this? If I look at white light, or this light behind the diffraction grating, white light, behind the diffraction grating, I'm going to see the rainbow. All right? So diffraction grating, you see the rainbow. Prism, a light goes through it, it reflects the rainbow. Even, like I said, a little piece of glass can reflect the rainbow on the wall. Why am I talking about this? Okay, because the scientists went to hydrogen gas, and they said, hey, look, it makes a color. Oh, that's cool. Then some other scientists said, oh, hey, look at this. I've been playing with diffraction grating. I'll look through, oh my goodness, what is this? When they looked at hydrogen gas through a diffraction grating, they saw something kind of like this. I'm going to just, oh, wait a minute. There should be green in there, right? Okay. I'm going to just say it's going to be this. They saw 4 visible lights. They saw this in the grating, So when you shine it through the grating or through the prism or whatever it will be, I'll just draw a little grating. Like imagine you look through a slide. You don't see the pure, well, you'll see like a lavender light, but you'll see a little reflection. And then you'll see something like this. I'm going to put a red line there. I'm going to put a green here. And I'm going to put, I didn't use, yeah, I did use green, I think. Then I'm going to put a blue here. I'm going to put a violet over here. Okay, so what in the world is that? Well, this is called a line emission spectrum. Now, here's the cool thing about this. This is a line emission spectrum. First of all, the first weird thing about it was, when I look at white light, I see a continuous rainbow. But I don't see a continuous rainbow. I only see 4 lines when I look at it through the prism or through the grating. I only see 4 lines. So what that tells us, only 4 wavelengths of light. Another word for wavelength for scientists can be color. All right, for when it comes to visible light, a wavelength of light will be a color of light. Red light, orange, green light, or almost like yellow-green light, blue light, violet light. Those could all be they are wavelength. They have a number for them as well too. If you wanted to really be, I don't have it with me, but really be nerdy about it, you could say something like, "Oh, look at that red shirt you're wearing," or "Look at that orange shirt. Look at that green shirt." What about, "Oh, look at that 760 nanometer shirt you're wearing," or "Look at that 580 nanometer shirt. Oh, I really like that 610 nanometer shirt you're wearing." Okay, well, okay, that sounds really bad and goofy, but every color has its own number. And as we talked about with Einstein and on the photon theory, there would be a limited number of colors. I mean, there'd be millions of colors, but still, like we'll just say a red, a pinkish red, or brick red, or a red orange, or orange red, or anything you can think of, any names, anywhere in between as you blend from invisible infrared into the red section all the way through the violet and past that. So it'd be good to look at a picture of a rainbow. All right, here's the deal. Make it long story short, I'm talking a long time about this. It's a lot to think about. But when you look at a gas, like hydrogen element gas, you see a line pattern. Anytime you look at hydrogen, you'll always see that pattern. So if scientists know now even, they can look at the sunlight, they can, pass the atmospheric gases because we have the atmosphere interfering with it. But actually, you might not even know that if you go past our atmosphere, the sun is not yellow. If you go past our atmosphere, the sun is white, like a star, like the starlights we see at night. But anyway, if you look at the sun past that, you would see that most of the sun gives this pattern because it's mostly hydrogen gas. And we can look at stars in telescopes, and we can tell what elements make up that stars, or what are the main components of the atmosphere based on what they see when they look at it through a telescope. Pretty neat. Okay, so this is a really cool thing I'm telling you about. But what I'm telling you is not anything new. It's new to you, but it's been known since early 1900s. But scientists did not know what in the world is happening there. What causes that to happen? Okay, so this led to the quantum theory after many scientists. And the scientist who gets the biggest credit for this would be Bohr, for mathematically explaining it. There were many other scientists before him. I don't have all the names. I'm not doing great justice to it, but but what I'm going to do is I'm going to kind of explain to you in a kind of a weird way what's going on. So I'll just say the spectrum is red. We're just going to say this now. It's not exactly true. Like the number, I don't think the color is, that's the wrong one. I'm just picking these 4 colors. I'm going to just pick these 4 colors. A blue, purple, or violet, we might say. Blue, purple, violet, red, and then I'll put a green. I think it's more of a yellowish color, but it doesn't matter. All right, so there are 4 different places. All right. Well, I saw an example of this story once in a book, and I'm going to use it. It was, and here's what they did. Okay, so that's the little spectrum you would see. Now, you'll see a different color spectrum for every element. And hydrogen only has one electron. Think about that, and it jumps. Well, we'll get to that later. But other elements with the more electrons you have, the more colors you see, and you see a lot more lines. So hydrogen is one of the more simple ones. So why does it have this pattern? All right, Niels Bohr is the one who came up. Well, Rutherford came up with the planetary model, saying electrons travel in orbits around the nucleus. But what Niels Bohr did was he said, well, there's something interesting about them. Electrons, when an atom absorbs energy, I've told you this in past lessons, the electrons will be excited, go to excite to a higher level. Well, they jump up to a higher level, like in photosynthesis. But then electricity or energy, heat, like electricity from the powering the light bulb, the neon light bulb, whatever, or the hydrogen light bulb. The electricity is going to cause the electron to jump up, and then it's going to fall right back down. Well, it turns out that according to Bohr, every element has sort of like, it's almost like the way, because of its nucleus and the levels it has, like it's programmed like a computer, that it's only going to give certain colors of light off. It can only absorb certain values of energy, and it can only release certain values of energy. So a little story that a book used once is there's a staircase, a little analogy I'll say. Now on this staircase we have Electron the cat. I named him Electron. So I'll just draw a little picture of a cat. I don't really know how to draw a cat too good. Sometimes it might look like a bat, but I'll put some little ears on it. It's not a bat, or it would have wings, right? But I guess that's cattish enough, right? Uh-oh. What is that one little place, like a one-eyed little cat looking at you? Red-eye cat would be good. That doesn't really, I don't know if that's really a cat. We'll just call that Electron the cat. So, like other, Electron is right now, we'll just say that it's on, it needs to be on a stair, actually. I better put it on a stair. It's on the ground level. We'll just call that the ground level. All right? So we'll say it still has to be level 1. Then we might have level 2, 3, 4, 5, 6, 7. We'll just make up some numbers here. But, on the stairs. Now, Electron is not like a normal cat. You'll see it's something strange about it. It's this weird thing that can travel through space and time. Okay? So it's not a real cat like we'd know. But if Electron was really, really low on energy, I'm hungry, and you say, well, Electron, we're going to give you all of this food. Electron likes to eat different light, different photons of light. Okay. So, like I'll just say, let's just say we have some red photons. We have some yellow cat photons. We have some green cat photons over here. Cat food. Okay. We have some orange photons. And we have some blue and some purple photons. I don't know if the purple show up that good on here. All right, well, anyway, you see a bunch of colors there. Okay, so here's the cat food. Well, what that amounts to for an atom or for electricity is like saying, okay, if I shine white light to this, okay, what's going to happen? The atom, when we think about that, like even with, as I talked about in atoms of plants for photosynthesis, well, atoms are picky. Each element, like a cat, is picky. All cats won't eat everything. They only eat certain ones. So every atom, as I said, is like made that it can only absorb certain photons of light. That's really weird. It's strange. Like when we saw that, I mentioned it in the very beginning. Not a good job of it, saying that when we heat this thing up, we see colors, but then it skips. And it skips all the way, like you see red, orange, and yellow color. Then it jumps to like being, maybe you'll see a bluish or purple color, but you never see an invisible color, and you never see green light when you're heating it up. Okay? Why do you never see a green light or in there? So what's happening is it does not absorb that energy. Energy, it's not like I don't know how to say it. it's quantized. That's the magic word they use for this. Energy is not continuous, but quantized. Now, the word quantized has to do with quantity. And so what it means is a cat, the atom, will only eat the red photons, we'll say for hydrogen, only the red, the green, the blue, and the purple. It can only eat red, green, blue, purple for a hydrogen atom, we're just going to say. So what happens is, even though I'm shining all blue light on it, and orange light, all these other colors of light are being shined on it, they are ignored. You know, they have no effect on the atom. Only the photons, only the particles of red light, red, green, blue, and purple. It's real strange. It's like saying, hey, I'm going to give you the brightest light in the world. I'm going to shine this bright white light on you like from the sun. You're getting every possible color, every possible photon of light is hitting you. But guess what? They're picky, and they only take, for hydrogen at least, only red, green, blue, and violet. Isn't that weird? Okay, but what happens to the atom? So, when an electron eats a red photon, suddenly, electron is going to be right here. It's going to jump to this level. I'm just going to move this level right here. I'll put it right here. So it's going to be right there for a moment. Excited. But now, imagine that every time it gets there, someone comes along and they push the cat over and he falls off, okay? We're not going to be mean. We'll say it's soft on the ground. But let's just say we're going to fall this way. So he falls off. When he falls off, just think the little cat falls down. And I'm not going to be abusing the animal. Remember, he's a cartoon science fiction cat anyway. So the cat goes down and he goes like, meow. Okay, like, meow. You push him off. All right, I'm going to put a red light there for a minute. But on the other hand, let's say that he eats a purple photon. Now, you remember Roy G. Biv, this is a high energy. Now, electron, the cat, is all the way up here. And now when you push it down, it's going to be like, now, you know, the cats are real good. They'll land. I don't know if you ever see a cat, like, pushed or whatever off of the side of something kind of high up. But the cats will always land on their feet. Very good. So like, so what I'm trying to show you, either from it being louder or higher pitch, that as it falls down, it releases light. As it goes from, it should only fall down to the ground level, but oh well, I made another ground level, I guess. But okay, we'll just put it to there. That's good enough. When the atom absorbs a red photon, the electron in hydrogen jumps to a higher level, then it immediately falls right back down. It falls down and gives off red light. Then the atom might absorb let's just say a green photon. Well, it'll jump to a level that's higher up. We'll put it right here maybe. And now when it falls down, it'll give you a green light coming off. All right, and then we don't have left blue. So the blue might be up here, close to red or whatever, and it falls down. And it gives you a blue light. All right, so let me just play around with electron configuration for a minute. And this is not really going to be true, but I'm just going to show you a sample of what we can just make something up for a minute. Okay, I'm just going to use these. I'm sure they will go higher even than this. So, when we talked about the excited state, when an atom is in the excited state, I put too many, the electron jumps. There's only one electron in a hydrogen atom. It jumps up. Let's just say it jumps up to here. Then it falls. How about we'll jump all the way up to 3? Actually 3D and 4s. 4s is actually higher, isn't it? Okay. That's okay. I won't mess with that. So say the electron goes from here. It absorbs energy and boom, now it's on this higher level. But when then it falls down, and you'll see we'll just say as it falls down, it gives off a flash of blue light. Or we might say, boom, it absorbs what we would call energy. It doesn't have to be color, but it could be electricity even. It could be electricity or heat equal to the value of a blue photon. So it takes the blue photon energy, that exact amount, or purple, I'll say, and it jumps up to the higher level, it falls down, and gives you a purple color. All right, and then, same thing can be true for the red. We'll just let the red be right from there to there. Or green. Green can be a little higher. We'll just say from there to there. So it jumps up and always falls back down, always falls back down. So, in the atom, why do you see a lavender color? Why do you see a pink lavender color? Well, think about this. If I have a sample of hydrogen gas, there are billions and billions and billions of hydrogen molecules in that sample of gas. So I'm just going to draw all these around and so forth. Now, it's actually H2, so you have 2 electrons, but it's okay. Now, here's what I wanted to show you. At any given moment, as they are constantly absorbing electricity, releasing, absorbing, releasing, absorbing energy, releasing energy, they can absorb it in terms of, they can absorb it in the form of electricity, but then they'll release it in the form of light. They can absorb it as heat even, and release it in the form of light. I'll show you a neat thing. Some chemicals, when you heat them up, like copper, which is blue, it gives off a blue color. And the same thing is true. And if you look at that blue color from the copper chemical, the copper chloride, for example, if you look at the blue light that's given off, when it glows through a spectrum, you will see the line spectrum. If you look at through a grating, you'll see the line spectrum. So you can see it from gases glowing, also from solids that glow and give off light. That's actually how they have fireworks, how they make fireworks. Okay, so here, let's go back to hydrogen. So let's turn this off. If this were turned off, you'd have billions of hydrogen molecules inside this glass chamber. Now, you turn it on. At any given moment, some of these are going to be absorbing and releasing red. Okay, some are blinking, like little lights blinking. Then, at the same moment, some of them might be blinking green, absorbing and releasing green, like they're going to that level and up. Some, and maybe hopefully get the hang of it now. Some will be doing like a purple, all right, and some will be giving you a blue. I think there has to be probably a little bit more in the red range. Well, I don't know if you noticed this, but you can go back to the video at the beginning if you wanted to see it. But when I made this color, I was only using red, green, blue, and purple, and I was just rubbing them all together to get this kind of a lavender color that you see right above. I mean, we know that red and blue give you purple, and you already have the purple here. And the green just made it a little bit, greenish or yellow makes it a little bit lighter. So that's the pinkish lavender color that you see for hydrogen gas. Okay, so, and again, this molecule might flash red right now. The next moment it might flash green, then purple, then blue, green, red, purple, blue. They're all doing this at the same time, and so you end up getting a mixture that looks like the color. All right, so that is why you see it. Now, if you want to see everything that I'm telling you, you ought to read this as well, but if you want to, here's an explanation of the spectrum. If you want to read on the notes, and I'll talk about the staircase as well. Everything I'm telling you is written right here, and there's also in your textbook. They'll also talk about it. Oh, the word quantum. So here's another weird thing about it. When the electron gains energy, like let's just say it absorbs a photon of light. The electron at level 1, let's just say it absorbs 1 and it jumps to 4s. Well, guess what? It doesn't fly up to 4s. It's at 1, boom, but it's at 4s. When it falls down, 4s, boom, but it's at 1. So it is being like transported from electron to cat. Even when electron to cat falls down, it doesn't actually fall. Even though I said knock it down, the cat is here, boom, then boom, wow, it's right there. The cat was here on this level, then wow, it was there. Cat was here, wow, then there. The cat was here, wow. Okay, so anyway, so however it goes, so they just go from boom, boom, boom to doom, boom to doom, doom to doom. Like kind of like you see the cat here, then you don't see it. It's like almost like it will be invisible for a moment. But it's like here, then there. Like I can't even do it with my hands, but like if I have one hand, here's the cat here, gone there. Okay, here I can't do it. I'm being too goofy. What am I trying to do? All right. Well, the cat rematerializes. It's actually good to use the example of science fiction. So like here you are on Earth. They beam you up to the moon. The very next moment, you turn into energy, and like as fast as light can travel, boom, you're in another location. Okay, you're here. Beam you to the Eiffel Tower, then beam you right back, or beam you to school. Beam back. So it's like you're in one place to another. You're skipping through space and time. That is called quantum leaping or quantum jumping levels. Okay, Niels Bohr explained this. If this is a lot, and I probably have about 10 more minutes to show you the math onto this stuff, and I'm gonna get this to you. I better just erase poor electron for now. You have some space. So here's what Niels Bohr did. The scientists knew about those lines for hydrogen. Actually, I think there are 5 or 6 lines for hydrogen. Each one has a certain number, measurable wavelength, and it always gives you those wavelengths. Well, Niels Bohr made an equation to explain the wavelengths, and it's this one. Negative 2.178 times 10 to the negative 18 over n squared. Now this is in section 7-8 of your notes. And it's joules, okay? Now, I'll tell you what, I'm going to throw in one more letter here. This is all you really are going to need. This many joules divided by n squared. Now, if you want to put a z squared right there on the top, you can also add that to the equation. And I'm going to tell you what that means in a minute. I've already mentioned something about z. You might know it means atomic number. Actually, let's take it away first. I'll bring it back in a minute and show you. Okay, so what Bohr was saying is this. In the atom, there are certain energy levels. Everything I'm telling you came before electron configuration, so it leads to it. This is level 1, level 2, n equals, they call it n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, n equals 7. Those are all the levels, and they go on and on infinitely, okay? And here's your nucleus. So Bohr was saying when an atom gains energy, its electron goes to an excited state to a higher level, like we just said. Then it falls down, and as it falls down, it releases light, okay? Different colors of light. The hydrogen atom has only, we'll just say these 4 lights. There's actually some that are invisible as well on the hydrogen. I think there's 6 lines for hydrogen, that 2 are outside the visible range. But anyway, those 4 lines that we saw, we'll just talk about those, represent 4 different excited levels to go up and down from there to there to there to there. And they have certain numerical values. So they have to always be going to the same level up and down and so forth. All right. Now, this tells you the energy the energy that the atom has when its electron is in this certain level. The energy it has relative to its nucleus. So the same way that I told you before, if I take the electron, and I'll show you this before, above, because of gravity, gravity's going to pull it down. Uh-oh, I better use my hand. Gravity's going to pull this thing down, okay? Well, the higher you go, the more, the faster it's going, the more energy it has as it falls down. So that's an important thing to kind of imagine. So same way with the nucleus, the farther you are from the nucleus, the more energy you'll have as you're going in and out. So, all right, now there's a negative number in this, and I'll show you why in a second. So let me do a calculation, and I'll just do one of these for you. On your paper, on your worksheet, you'll do n equals 3, 4, and 5. I'm going to do letter A, n equals 1, n equals 5. All right, letter A says this. Calculate the energy of an electron located in the following levels of a hydrogen atom. I guess you can call it the energy of the electron. All right. I like to say the energy an atom has when its electron is in the following level. No, the energy a hydrogen atom has. That's another thing. What I'm showing you, this equation only works for the hydrogen atom. So it's not 100% true. But the concept behind it lets you see, you understand the whole quantum, the line emissions, you understand the wavelength frequency concept. You'll see what I mean by this. So this only explains the hydrogen atom, or any atom that you, say if you have hydrogen, if you have helium and you take away an electron, you have helium plus 1, well then it would only have 1 electron. Or what's the next element up? Lithium has 3 electrons. If I take away 2 of them, okay, and have lithium plus 2, this will also work. So that's why I told you, you can actually put in Z, which is the atomic number, and you square it. This times Z squared, and it always works. So it works with any atom in the entire periodic table, as long as that atom or ion, as long as that atom or ion has only 1 electron in it. So if you take away all the electrons, this will explain what's going on. All right, so we'll just keep Z as 1 for hydrogen, so there's no need. We're only going to be talking about hydrogen. But if you were to see something like, say, helium plus 1 or lithium plus 1, then technically you'd have to throw in you have to put in Z squared. So you don't really have to have that in here. We're only for hydrogen. But it will be given to you if not. I don't think you have to worry at all about seeing that on AP. They could give you the equation and ask you a question, but they'll give it to you. They won't expect you to know it. But just know that the Z would be the atomic number squared. All right, at level n equals 1, the energy is going to be simply E at level 1 is equal to negative 2.178 10 to the negative 18 divided by 1 squared, which is 1. So it's the same number, 10 to the negative 18 joules. So at level 1, it is negative 2.178 10 to the negative 18 joules. That's how much energy the electron has, or the atom has, when the electron is in the level 1. All right, for n equals 5, that means, so you were at level 1, 2, 3, 4, 5. Now you're at level 5. If electrons at level 5, how much energy does it have relative to the nucleus? It'll be E at level 5 is equal to, let me do that so I don't mix it up with my math. E at level 5, I use that, equals negative 2.178 10 to the negative 18 joules divided by, this time n is equal to 5, so it's going to be 5 squared. Okay, so that's 25, right? So divide it by 25. Uh-oh, I need some light. Okay, 2.178, I need some photons of light to power this calculator. 2.178 10 to the negative 18. Oh, by the way, okay, yeah, I had it right. Divided by 25 is negative 8.712 times 10 to the negative 20 joules. Now, notice there's a negative value in there. Don't worry about that yet. You're going to see why in a minute. Negative is part of the equation. Like level 1, negative 2.178 10 to the negative 18. If you were at level 2, you just put a 2 squared, divide that number by 4. Level 3, 3 times 3 is 9, divide that number by 9. Okay, and that's what you'll do on the first part of the worksheet. The homework will not be too long on this. You're just going to do 3 calculations on the top, but then you got to do 4 on the bottom, and I'm going to show you how those are. Actually, yeah, 4 or 5. Okay, so 8.712 10 to the negative 20. I better write that down. At level 5, 8.712 10 to the negative 20, and then level 1 was, what was it? Negative 2.178 10 to the negative 18. I can remember those two. I just need to remember them because you got them written on your paper, hopefully, but I'm just putting them on the chalkboard. Okay. Now, so that's the first equation that you need to find energy at each level. Then the next question, and on the worksheet that you're going to be doing, it says this. Calculate, number 1, the minimum energy of the photon of light associated with each transition. So it says this. Oh, I'm sorry. I did A, and B for you, 1 and 5. Let's go down to B now. It says this. Calculate the wavelength of light associated with the following transitions occurring in a hydrogen atom. And I'm only going to do A. If in the hydrogen atom, if the electron goes from level 1 up to level 5, then tell me what is the wavelength of light that's associated with that change. Now, to answer that question, I'm only going to do this one, and I should have given you more space. You're going to need a lot of space. You might want to write it here and even there. I won't do the other. The other will actually be the same thing, but the opposite negative number. But anyway, I'm going to do this part right here. And what you'll do, you're going to have to make 4 calculations, and they're the ones that are listed on this paper. So these 4 things that are on the worksheet. Number 1, calculate the minimum. Number 1 says, calculate the minimum energy of the photon associated with each. So the energy of the photon, remember we talked about this equation? Energy of the photon equals HV. Well, there's another way to calculate energy of the photon. And that's going to be equal to the change in energy levels. The change in energy from level N initial, well, in final minus N initial. Okay? So the change in energy will be equal to E final minus E initial. So in this is an equation that's not given, And this question is not even given on the AP. I will give them to you, especially for general chemistry. So what is the energy of the photon? Well, it will equal the change in energy, which is E final minus E initial. So that means for this particular problem, it says, I'm going to do on the paper, when you go from level n equals 1 to n equals 5, what's the energy involved? All right, if I'm going from level 1 to 5, 1 to 5, I start at 1, I end up at 5. What's my final? My final is level 5, and my initial is level 1. So I can say E final minus E initial. I can also write that as E, well, I'll just leave it there so that in case you want to look back at it later. E final, E5 at level, yeah, you go from 1 to 5. Energy at level 5, energy at level 1. So I'm going to put these numbers in. So watch this. Change in energy equals, at level 5, it was negative 8.712 times 10 to the negative 18. No, 10 to the negative 20, sorry. We just calculated that up above. Now I'm going to put negative, and I'm also going to put parentheses, minus negative 2.178, 10 to the negative 18. Now, if you really, really, really want to be good, significant figure AP students, okay, and I won't mind much for the general, but you know, you don't have to do this, but watch what you can do. Remember, change them to the power of its higher. So if it says 10 to the negative 20, you can make it 10 to the negative 18. You can say, well, that would be like saying 8, wait, how would you do that? 10 to the negative 20, 2 to the negative 18. So it'd be 0.008712 times 10 to the negative 18. You don't have to write this step down at all. That minus negative 2.178, 10 to the negative 18. You don't have to do this. Let me just, in fact, to not scare you, let's just do this. In my calculator, type this in. Now be very careful that you can type this in. Negative 8.712, it has to be negative on the calculator. 8.712 negative. But then 2 times 10, exponential 10 to the negative 20, minus 2.178, exponential negative 18. So just ignore that yellow line, that mess I wrote there. This minus this equals 2.091, 10 to the negative 18. Now, for sig figs, I'm probably going to be okay, but it would really be the same as like saying 0.008712 minus 2.7178, sorry. And then I get 2.169. Wait, 8.712 exponential 20 negative. Oh, minus, I'm sorry, I got the wrong answer. And I can see what I did. I think I did. I forgot to put, did I put my minus in? Okay, that's why I read it written there. 8.712 negative exponential 20 negative. So it should look like that on your calculator. Negative 8.712 to the times 10 to the negative 20 power. Now push the minus button on your calculator. Minus. Very important. Now put in 2.178 negative exponential 18 negative. So it's got to be, you're minusing and then you're putting that number in. So a negative minus a negative is a negative minus another negative is a negative plus that next number. And so, yeah, actually I did have it right, but that's okay. At least I went through and shown you. It's a positive 2.091 10 to the negative 18 joules. Now, okay, 0.00871. Sorry, I'm just trying to do something here. That's a negative number too. If you're trying to, I'm going to tell you why I wrote that down. This is only for AP. You can skip ahead a little bit if you don't want to see this, but okay. 0.00871 negative minus Well, did I write it down correctly? I was only trying to do this to show you what your sig figs would be. That's why I was trying to do this for AP. And 10 to the negative 20 would be 8.712 10 to the negative 20 is the same as 0.08. I wrote 0.08. That's why I got it wrong. It's the same as 0.08712 10 to the negative 18. Okay, I typed the number in wrong. 0.08712. This is tedious math, you can see. Okay, and now I get the correct answer, 2.090. And actually, you know what? In the sig figs, the box rule says I should go to that value, the 2. And on this one, the box value says I should go to the third number after the decimal, which is the 8. So here it's the third number, which is 1. So in other words, it doesn't really matter. And I know I told AP a lot of times, when in doubt, for sig figs, just put 3 sig figs. Well, in this case, I put 1 after the decimal. If you put 2.09 on the AP for a question like this, and not 2.091, you will get it right. In my class, I mark off and say, hey, you should be careful with it. But in AP, you'll be right. You'll be right too. You'll be correct. They'll let it go. That's what I'm trying to say. But I didn't have to do this, so I just took a little time. But to prove it, the box rule, that's the box that would be your answer should be in, going to 2.091. That is the correct answer. That's the best answer for AP or for my class. But if you on AP, if you put 2.09, you'll be okay. I guess I'll let it go too. Yeah, for this one problem. I don't normally give you an extra sig fig. But okay, so 2.091, 10 to the negative 18 joules. Now, another thing you need to notice is this number is positive. Why does that matter? Well, positive means it is endothermic. Endothermic means you go from one level, you add energy in order to get it up to level 5. To go from level 1 up to level 5, level 1 up to level 5, do I have to add energy or is energy released? Now, this might be a new thing for general students, but if I add energy, if I have to lift it up, I have to use my energy, that was a positive. Energy was positive. But when I release it, energy is, when I let it fall, energy is released. It's called exothermic. Endothermic is when you raise it to a higher level. Exothermic is it falls down. So if you release energy, watch this, it releases light. We know that red or green or purple or blue light, it releases light that's exothermic. It would be a negative number if it releases light. It doesn't. It absorbs light. So to make on an atom, what you're basically saying is to go from level n equals 1 up to level n equals 5, it has to absorb a photon of light equal to 2.091 times 10 to the negative 18 joules. That's what we're saying. If I gave a positive value, 2.091 to a hydrogen atom is sitting there, it's electrons at level 1. You give this photon to it, like the cat, it eats that thing. It's probably the red photon, I would call it. So it will jump. Suddenly it'll be at level 5. But then the very next, it's excited. Okay, and that's all that we did in this problem. Now the next moment it's going to fall down. It's going to release light. Okay, but we'll show you that part in a second. Okay, so the energy of all of this work to tell you, the energy of the photon is 2.091. I'm going to erase this. 2.091 10 to the negative 18 joules. Change in energy. The energy of the photon. I'll just say that. E photon equals 2.091 10 to the negative 18 joules. Now, when you're doing a problem, if for some reason you get a negative number, that's still true, but on the next step you're going to make it positive. All right, the next question, all right, that is part 1. Oh no, there's 3 more things, but you're going to love them because now it's going to get very easy. Number 2 says, what is the maximum frequency of the photon of the maximum frequency? Well, guess what? Energy of a photon is equal to h times frequency. So 2.091 10 to the negative 18 joules. Oh, what a mess. Is equal to, remember Planck's constant, 6.626 10 to the negative 34 joules second times the frequency that would look like a V. All right, it's the same problem we just did in the last lessons, the easy math. So now just divide both sides by that. It's hard for me to write at that level, that far down. 2.091 10 to the negative 18 divided by 6.626 10 to the negative 34. 3.15, no, 3.156 times 10 to the positive 15 is your frequency, and the unit should be Hz, hertz. So 3.156 10 to the 15th hertz. Now, what I was saying earlier, when you do your homework, if you've gotten a negative number here for energy of a photon, the change in energy, okay, technically, the change in energy can be negative, but the photon itself would not be negative. The negative is just telling you that the photon was released. Positive, in our case, they were positive, it was absorbed. So for this problem, if you get a negative number here when you subtract them, that will tell you, oh, it's exothermic. The electron falls down to a lower level and it releases light. If you get a negative value, that's the only thing you need to know, that it's telling you the electron falls down and releases light. But when you calculate the photon frequency, then what you're going to do is you're going to just make the number positive. Just if it had been negative, just make it positive. You can't have a negative frequency. That's what I'm saying. So make sure your frequency is always positive. Okay, so we got the photon energy. Now we have the frequency, and the frequency is equal to 3, I'll just write it here, 3.156 10 to the 15th, Hz, hertz. Now let's find the wavelength, number 3, and I think you know how to do that. Lambda nu equals c. So if you might not have to really watch all this stuff now. I know it. 1 was that. 2 was find the frequency. 3, let's find the wavelength. Lambda nu equals c. So the wavelength, if I know the frequency is 3.156 10 to the 15th hertz, and I know the speed of light is 3 times 10 to the 8 meter per second, then all I got to do is divide both sides by that. 3.156 10 to the 15. Wow, it's hard to write my numbers on this chalkboard at that angle. Okay, so 3 times 10 to the 8 divided by 3.156 10 to the 15th power is 9.506 10 to the negative 8 meters is your wavelength. Your wavelength is 9.506 10 to the negative 18 meters. That's the third thing you need to do. I hope you're not getting lost on this, but I'm only doing letter B. I'm only doing part A. If I go from n equals 1 to n equals 2, I want to find out what is the wavelength. Oh, actually, I'm finished with this question. Calculate the wavelength associated with each light, and that would be it. It would be that right there. Okay, so first you found that subtract them, the two energies. First you found the energy level 5, level 1. You subtract them to get the energy. Then you take the energy you plug in to find the frequency. Then you plug in the frequency to find the wavelength, 9.506 10 to the negative 8. Then, only for AP students, there's one more question, and it says, what is the minimum energy for a mole of photons in kilojoule per mole? All right, there's one more thing that you get to do in AP on the worksheet. It's not on it should have been here. You can just write on this paper. Yeah. But anyway, here's what you do. To find the energy in kilojoule per mole, I did it already for you in the last lesson, so it's the same thing. First, we'll take the energy. If you have 2.091 times 10 to the negative 18 joules per photon, the energy of a photon is this. If I have that many joules per photon, 10 to the negative 18, try to make we can see that. What will that be in kilojoules per mole? This is really important, AP students. Really, really important. I know you're like, oh no, it's been an hour. We're almost through it. Okay, so here's what you do. Joule to kilojoule, you just use 1 kilojoule equals 1,000 joules. That would give me kilojoules per photon. And then we don't want per photon, we want per mole. So I want to have mole on the bottom, not photon. So photon goes on the top. Whoa. So 1 mole is 6.022 10 to the 23rd photons. So you take that number, 2.091 10 to the negative 18 times 6.022 10 to the 23rd equals, divided by 1,000, and it will be 1259 kilojoules per mole. I'll just tell you one more thing real quick. When you do your homework or do a problem, when you subtract final minus initial, if your number is negative, if it were negative, it's not here, then that means this also has to be negative, and it also means that your answer here would have to be negative, okay? For this part, it would matter. But your frequency will not be negative, your wavelength will not be negative, and that's all. Yeah, that's all you need to know. So energy could be negative, and that would tell you how much energy, that would tell you that 1259 kilojoules are released per mole, or 2.091 10 to the negative 18 joules released per photon. Okay, but in this problem it wasn't. Okay, all right, you guys, that was a long one. I'll see you, though. The homework is fairly short, I hope, for that. I'll see you.